talk today, I'll start out by giving you kind of an introduction to what metals needs we have for manufacturing science. Then I'll give you guys an overview of the science that we've been working on to look at enabling metals extraction in a sustainable way. And then I'll give you some insights that we're starting to get into to look at sustainable approaches to metal 3D printing. So totally on the other side of the supply chain, thinking towards how do we get more bang for our buck out of the materials that we already use to work out some of the challenges in strength to weight ratios, for example. And then I'll close with a little overview of the really fundamental science work that we do, looking at structure, property, relationships, and the defects that allow those to work or not under different technology performance conditions. Right, so getting started, of course, as a material scientist and metallurgist, I always have to go back to steel and the Industrial Revolution. So when we look back at developments and innovation, developments and innovation in quality of life and technology over the centuries, we see that really these innovations in manufacturing have been game changers in evolving what we get out of our technology. So what do I mean by that? Well, in the Industrial Revolution, we see kind of the birth of these massive explosions of increase in quality of life, where we now see the industrial production of steel at these massive quantities that start to allow us to create, indoor versions of stoves and things like that that are now able to be manufactured at bulk scales for every single house out there. Then we see in the 1800s, we now start to have all metal machine tools like screwdrivers and other types of saws that also are game changers to quality of life as a whole. And over the years, there have been other advances like electrical energy, plastics, integrated circuits, and various different things that each one of them, we can see massive changes to quality of life and to what we expect out of our technology in every step of the process. But as we look right now towards what our future entails, we also can see that there are some new challenges ahead of us. In particular, challenges about sustainability. So when we ask ourselves, well, what are these challenges? What do they really look like from a technical perspective? We can kind of characterize this in a few different ways. The first of these is asking ourselves just the basic question, going from the raw materials that we get out of the ground to the energy output or the actual material and part that we need, how much loss do we have? And you'll see it's actually incredibly substantial. The amount of energy used, the amount of material that is lost is very high. So the waste streams are very high in our technology used today. Similarly, if you look at the greenhouse gas emissions that we all know are warming our planet, even on cold days like today, of course, I don't want to undersell that electricity and transportation are really critical. We cannot get anywhere forward without acknowledging that those are the main brunt of decarbonization needs. However, I also want to draw your attention to the fact that industry is also nearly a quarter of our emissions today. So if we overlook the deep emissions that come out of the industrial sector, then ultimately, once we decarbonize electricity and transportation, we're really going to be screwed. Excuse my language. So what do we need here? Well, we need new manufacturing technology that's not just looking at, it's not just looking at, how do we engineer the next generation of technologies, but also asks ourselves, what is the science that is required to enable this transformation? So as a material scientist, I like to think about this from the scale of atoms all the way up to reactors. So at the atomic scale, we think of the performance of a device based on the individual atoms and how they bond, how they are connected, that describes the underlying foundations of what a material is. When we zoom out into the continuum scale, to understand, for example, if a bridge is going to fail or work, we have to understand the properties of that bridge, say its mechanical strength, its yield points, its fracture loads, And all of that we can define based on some voxel of material or morsel of material based on models that describe it. So that defines the smallest and the largest scales, but to be able to get the physics of that material at the atomic scale, the highest dimensionality view of this picture, to match the continuum picture of did the bridge work, yes or no, we need to be able to capture all of the representative length scales that describe the dynamics of the material. So of course that demands some sort of a effectively reduction of dimensionality over 10 decades of length scale and 15 or more decades of time scales, from femtoseconds to years. So in material science, this is the age-old problem that is the foundation of our field. It is called the mesoscale challenge of finding ways of connecting atoms to the bulk scale performance of a part of the material that ultimately defines for us whether or not it will perform the way that we need it to. In my group, we study the mesoscale challenges of material science from two perspectives. One of them is tuning properties using an understanding of dislocations, which are the line defects that ultimately are responsible for whether a metal will become stronger or fail. And mass transport that describes in a moving system or a heating system how ultimately the flow of energy and mass dictate how a system will perform over time. So this is the overarching view of what my group does. We develop a modern toolbox of advanced microscopes, detectors, and artificial intelligence for analysis and control methods. And we use all of that to understand metals processing science, so the very fundamentals of why metals become strong or fail, as well as refining processing, like when we anneal a metal, how can we design the properties we want? And then we extend those really fundamental views to sustainable and applied technologies, looking at resource sustainability, so that's iron and steelmaking, as well as some critical material types of extraction problems. And at the other end of the supply chain, we look at metal 3D printing and ways where fundamental science can enable big advances towards new types of technological paradigms. So, armed and ready to go off to the races now. Let's get started at the beginning of the supply chain, looking at metals extraction science. So, again, as a good material scientist, we always have to start with steel. So steel is ubiquitous in society. Raise your hand if you encountered steel at some point today already. Nice. Anyone want to say what they encountered it with? Feel free to call it out.
I bet these benches are made of steel.
Bet there's a lot of steel there, yeah, in the benches. How about the building? So there's usually steel girders that hold the building up. Any of you drive a car here? So the frame of your car is probably steel. And let's see, anyone take a train? Wow, nobody took a train. Well, if you had taken a train, the girders of the train are typically also steel. So in all of our technology, we see steel as the go-to alloy, the thing that we have known about since the Industrial Revolution, and we produce at such massive scales that in fact, we can always rely on there being some sort of a steel that will solve whatever problem we need. Great. Well, that's true in, the transportation industry, it's true in the construction industry, in all sorts of places, including, by the way, the construction of renewable energy, and all sorts of pipelines that we need to be able to rely on for our infrastructure. However, steelmaking currently accounts for 8% of the CO2 that we emit across every single industry over the whole world. So it turns out when you look a little closer at that, you realize that actually that number is only continuing to go up by about 35% anticipated by 2050. So you might ask yourself, well, where is this footprint coming from? This is a footprint that we might not even interact with in our everyday lives, right? All of you guys use steel already today. but you didn't necessarily engage with the carbon footprint that was implicit in the technology that you were using. So these are kind of the three main ways that we produce steel today. The first two are called primary steelmaking, i.e. we take rocks out of the ground and turn them into steel. And the other one is recycling steelmaking, i.e. Secondary steelmaking. So in each one of these, you can see there's kind of three main steps. Step one, we process the raw materials, take rocks, turn them into pellets that we input into our reactors. Step two is iron making, i.e. rocks into iron. Step three is we make steel. We turn iron into steel. So if we look at this based on the market share versus the kilograms of CO2 per 1 kilogram of steel, you'll see there's a lot of variation here. So the market is 71% basic oxygen steelmaking, which is the oldest trick in the book, the way that we perfected starting in the Industrial Revolution, and still to this day is most of our market for steel. About 5% is this budding new direction called direct iron reduction that I'll talk about in a little bit. And then recycling steel is the lion's share of the better way of making steel in terms of carbon footprint. But you'll notice there's still a fair amount of CO2 that's produced there as well. So you might ask yourself, 2.2 kilograms of carbon dioxide per kilogram of steel, where is that coming from? So we can actually do, of course, a life cycle analysis to try to get some understanding of where the emissions come from. And for one particular plant in China, this is now showing you for this basic oxygen steelmaking, where the carbon emissions come from in each step of this process. So now the first two here, your raw material steelmaking is, the blue category here. And this huge section here is one step of the process. The blast furnace we use to take our rocks, our ores, in that pellet form and turn that into molten iron. So that is 67% of this carbon dioxide footprint. So of course we can see that if we want to make a big impact in this field, figuring out how to address this one middle step of iron making as a decarbonization actually is probably the best bang for our buck in terms of our efforts spent. So the strategies to decarbonize iron making are quite varied and challenging, but I should mention that it's important to think about this based on time scale. So in general, of course, what we would all love to have is carbon zero. No CO2 generated at all, only sustainable products or fully recycled. We all, hopefully in this room, understand that in and of itself makes a challenge. But in the field of steelmaking, the fastest translation from an idea, a concept on the benchtop, to something that was rolled out and deployed, ready to go out at the 100 kiloton per year scale that is required to, as my colleague quotes it, be relevant in our field. Takes, let's see, the record is 17 years. So finding a way to translate in this really risk-averse industry from the current very carbon-heavy approach to something that's truly carbon zero is usually estimated as about a 50-year transformation. So if we put all of our eggs into that basket, by 2050, we're sunk. So this means that we need to think about this as kind of a transformational technology. So currently we have about a $2.4 trillion investment in the modern today's steelmaking and iron making infrastructure that we have out there. So of course, the first step is, you might ask yourself, what's the carbon footprint of what we have today? Could we clean that up? And the answer is absolutely yes. So there's a lot of carbon capture strategies that could be used to vastly improve the carbon footprint of the technologies we have today, helping to at least get us closer to the finish line as we, for example, continue to go through the various different technology cycles over the lifetime of, say, a 50-year reactor. So these reactors typically cost about $1 billion to build. You're not going to convince a country to shut that down after it's just opened, but you might be able to convince them to phase it out over time and to build a new infrastructure in these new technology areas in a way that, of course, you can also try to clean up the systems they already have. So then there's a way of, looking towards a reduced carbon kind of new technologies that can help to build up that infrastructure for the next generation, i.e. the transitional technologies that help to get us started. Not to say, let's just tear down all the reactors and start over again, but is there a reactor that we could build that is lower risk and will still have a return on its investment, but that will get us started on building the technologies that will get us to carbon zero emission? So this type of transformation is the way that I honestly see this going for the steelmaking industry. And the important point here is that no one solution is actually enough for the urgent timescale of climate change. So we actually have to be working on all three of these in tandem. So I'll be talking today about the work we've done on green hydrogen direct iron reduction. So looking towards that technology. So this is the key player that has caused the big carbon footprint that has created such an awesome advance in steel in society, but also has really created challenges in the carbon emission. So to be able to get our hematite ores that come out of the ground into iron metal requires a 3-step reduction process where we, in each step, evolve oxygen and effectively reduce the iron a little bit more. So if we do this with carbon monoxide, i.e. we have this blast furnace that, by the way, I can't actually even put a person on the scale. You wouldn't see the person because this is so big. Typically the scale that's helpful to see the size of this is if you put a forest next to it. It would be about here with the height of the trees, just in context. So these massive, massive blast furnaces, what you're doing is really you're loading in layers of, or alternating layers of iron oxides and coal. And what this does is we now blow hot air from the bottom, is that it creates activated CO that then with a whole bunch of heat that's also generated by the coal, ultimately gives us this thermal runaway that enhances the extent of the reaction and makes the whole reactor be really in continuous flow. And these, as I mentioned before, can run for like 50 years before you have to service them the first time. They are a really, really good way for our country to have a really stable economy and infrastructure for producing technology. So if we were to simplify this, instead of making CO2 come off, have it be H2O, of course, this makes the reactor a little bit smaller. Maybe simplifies life, right? You're just switching the reagents. But you'll notice that actually now this creates a really, really, really uphill reaction, where now we have an incredibly endothermic system, i.e. every time the reaction goes to completion, one time, you suck out 4 times the amount of heat you would have generated if you had done this with carbon monoxide. So what does that mean? In our really high temperature reactor, you're basically shooting yourself in the foot every time that the reaction goes forward. So this means that now we have a much higher investment required for energy and a much more difficult reactor to design in terms of continuous flow reaction. So ultimately, this has meant that although direct iron reduction was first tried in 1954 at a pilot scale, still to this day, it is at the pilot scale, just exploring if it can actually start to have highly subsidized versions of a product that they can bring out. So beyond just the chemistry being challenging, it's important to understand that actually one of the big challenges here is scaling up the problem. Because this last step here is not as trivial as you might think. This last step here actually creates a really sticky thing called wusta, which causes all of the iron particles to start to stick together. So ultimately, it creates what's called whiskering, where the pellets form these iron little whiskers that float across and stick together, causing now the entire thing to turn into all of these pellets in just this stuck little category. So now, instead of having continuous flow of our reactors, we have a stuck reactor that has to stop, and that millions of dollars have to be spent on carving out all of the iron that got stuck to the reactor vessels. So ultimately, if we want to design this reactor efficiently, we need to find ways of scientifically averting the sticking mechanism. So I should mention that sticking is averted today largely by a mystery spray people put on their pellets that usually works except when it doesn't. And when it doesn't, nobody quite knows why. But it costs several millions of dollars, if not tens or hundreds of millions of dollars. So as an investor, that's not exactly what we want to be doing, right? So the challenge in this, and the reason why, although this is not a new problem, it's still a challenge for us to understand, is that when we look at the entire scale of the whole reactor, i.e. the reactor stopped working, versus the smallest scale of the actual atoms, in fact, this is exactly the opposite process. The scale of the atoms, when we go from the oxides to the metal, we actually have a 46% reduction in volume. Whereas at the scale of the pellets, actually they swell up as they become more porous. And ultimately, the reactor stops moving, or stops flowing, because all of the pellets get stuck together. So connecting these scales definitively is really the challenge here. So in my group, we work on connecting these scales to understand kind of the most fundamental view of how we could control these reactors. From looking at the fundamental science of hydrogen reduction to a way of now creating new approaches to use light to drive this iron making forward, to finding ways of building models for these reactors that can describe the performance trade-offs as they react. We'll try to give you a very brief rundown, as I want to make sure we have time for everything. So in this work, we started off looking at these industrial these industrial iron ore fines, so that's without any pelletization. And we discovered very quickly that there are these tiny, tiny nanoparticles that actually we know very well should not react the same way as normal bulk materials. So we decided to look specifically at just those nanoparticles to understand how the nano behavior, the nanochemistry would alter the progression of this well-studied reduction reaction. So we did some X-ray diffraction and were able to validate that, in fact, it's a good surrogate system to be able to describe kind of some of the smallest length scales in this problem. So armed with that, we then went to understand a little bit more about how the phase transitions progress, i.e. the chemistry. And we were able to do that using an X-ray based operando experiment, where we could study with our X-ray beam information about the crystal structure, so the phases that are generated, as well as the drain shapes, i.e. are we sticking and smooshing together, or is this evolving in some sort of a way, still as the powder? So with that, we can start off by looking at the kinetics of the process, and we can see that at the highest temperature, it's a fast reaction that we generate all the iron we're going to, almost instantaneously, whereas in the other temperatures, we start to see that it's slow until we actually see a separation of the kinetic steps. So with that, we were able to then, at the very lowest temperature, separate these out into a more streamlined approach, and we were able to observe how each of the phases grow in as a function of reaction time. So as we did that, we observed the formation of woostite, even at 300 Celsius. Now, I didn't draw too much attention to it before, but actually the woostite phase is not supposed to form below 590 Celsius. And in fact, you might say, well, nanoparticles, anything goes. Usually the surface to volume effects, i.e. there's way more surface than there is volume in a nanoparticle compared to normal materials. Well, in fact, maybe that should be causing some way of stabilizing that woostite phase. But in fact, there's actually these lovely science papers from the 2010s that demonstrated that, in fact, it should go in exactly the opposite direction. In fact, it should be destabilized by the surfaces. So we dug in a little deeper and tried to understand what exactly is going on. And what we found is that actually, although we like to describe this as just a simple system, one phase to the next phase, the phase actually is not the same in every direction. And so ultimately what we found is that as you resolve the directions that are relevant to this material, you see that actually the rate of consumption of each species is different along the different crystallographic axes. So we were able to characterize based on this that in the first stage, for the first 50 minutes, we see fast chemistry for all reaction steps. In the second stage, we see primarily conversion from the magnetite to the bluesite. So that's the first step of the reaction in this case. And in the third step, or the third stage, we see steady conversion of all the oxide phases to metallic iron. So when we look at this and we see how actually in the first two stages, there's very strong dependence along the crystallographic direction. You might say, wow, this must mean something really weird. But actually, this is well understood in the field of nanoparticle catalysis that, in fact, when you have so much of your material as surfaces, the type of surface matters a lot. And so, in fact, this actually correlates very nicely with the classical catalysis literature, which nicely validates for us that these mechanisms are going exactly as you would expect. However, what you'll notice is that actually on step 3, suddenly that mechanism no longer really depends as strongly on the orientation of the crystal. So that tells us now that the crystallography has less to do with that last step. Something is happening potentially at a larger length scale. So Shubetsha and my group then went a step further and did an imaging experiment called X-ray technographic tomography, which effectively is a way of giving us a view that can go down to 30 nanometers in resolution, but can also resolve based on electron density, i.e. it can give us information about whether we are in a metallic state or a oxide state at any little spot within our material. So to do this on that 30 nanometer size, or I guess 36 in this case, we can imagine that either we have a bunch of little particles that may be packed and have some air, or we might have something that is the highest possible density, i.e. it's fully packed with material. So we did a whole bunch of combinatorics to figure out all the possible densities that could be present based on different combinations of this. We found that there's a cutoff here. So the electron density per voxel here is below a certain value, has to be an oxide. If it's above a certain value, has to be a metal. I.e., you could not possibly pack that many electrons into a single space unless you had a metal. So you'll notice here that if we look now as a histogram, looking at all the different voxels that make up the different samples from our interrupted run, we end up now with at t equals 0, fully oxide. At t equals 2.5 hours, we have a bimodal distribution. But you'll notice the first mode is showing us a higher density oxide, i.e. it's showing us that we have sintering. The second one is now showing us that we formed some of the metal within each of those voxels. So this is demonstrating to us that at 2.5 hours, we start to have the nucleation and growth of a metallic phase, as we also are sintering our oxide. So this is characteristic of that sticking I mentioned before at the reactor scale. So now let's actually look at some pictures, and what we see is that we start off with these beautiful particles that show us effectively nothing at all, because we can't really see the particles. They're just too small for us to be able to resolve at this point. But as we start to now zoom over in time, we now, after 2 hours, see this thresholded view where everything blue is now an oxide and everything orange is a metal. So you can see now these new spherical particles that are starting to form internally inside of the iron that correspond to actual iron formation, i.e. this is the nucleation and growth of that phase we're all hunting for in this iron-making process. And then finally, we end up seeing at the very end this 3D structure where actually the length scale here is much larger. So we see now a 100-fold increase in the size scale that corresponds to the iron alone in this material, and that corresponds now to just the metallic phase. So our view of this is really that what we've been able to demonstrate is fast transport of surface chemistry. The beginning, then diffusion limited chemistry in the middle in stage 2, and finally the sintering and iron formation that ultimately is associated with the whiskering at the nanoscale. So the important take-home message from this study has been that the nanoparticles that historically we've always thought of as too small, we don't need to worry about that at the scale of a meters tall reactor. In fact, actually, these can create some of the sticking phenomena that are so crucial to describe the performance of the reactor. And in fact, if we miss that, we're missing some of the instigators that could be causing a reactor shutdown. So this kind of gave us a key insight that we now need to find a way to incorporate the nanoscale of these processes into a way of describing the full reactors. So Shivecha, in her PhD work, said, well, it's great that we can, in the introduction to our paper, say, well, we should really get back to reactor models, but she felt that we should really just do it. We should say that we're going to do it. So she went off and asked herself, in these actual reactors, how can we describe nanoscale elements that would be present in a way that would allow us to have a model with an analytical solution we could actually solve? So in fluid dynamics, computational fluid dynamics, which you would usually use to describe this type of really, really massive reactor system, typically you don't have a way of describing things at the nanoscale without having a problem with the size of your simulation, i.e. you actually can't get it to converge, or it's so incredibly long in duration that you could never get it to finish. So we looked into understanding how we could connect that nanoscale size, this time in pores, instead of looking at the agglomeration, and use that to understand the flow of gases through the reactor. So, of course, if you have a reactor that's not stuck, i.e. there's good permeation of gases, then effectively your gas can get to all the different pellets that react in your system, i.e. you can go to completion in your chemistry. Whereas if you don't have good permeability in your reactor bed, ultimately it will fail because you will ultimately have the gas only going through the path of least resistance to get to the end of the reactor. So she felt that permeability was a nice proxy variable to be able to describe at a larger length scale how the attributes of porosity at the nanoscale would translate to reactor design variables that we. So armed with this, she then took a micro scale industrial pellet. Try that again. She took a micro scale computed tomography, X-ray computed tomography scan of a three-dimensional pellet and was able to characterize the structure of pores that were within that. Then she, with a set of collaborators, was able to get a small piece of a related type of pellet, and then get a view with 30 nanometer resolution as a function of time through the progression of the reaction. How does the three-dimensional porosity evolve? And with that, she was able to use a mathematical model called percolation theory, which describes the connectivity of connected networks, to be able to effectively describe how the flow of gas through your system will evolve based on the connectivity of the pores in your network. I.e., if you have a non-percolated cluster, you have random porosity throughout, the gas isn't going to get very far into your pellet. Whereas if you have now a fully percolated cluster, so that you can blow gas from one end to the other with nothing in the way, in fact, that actually causes like several orders of magnitude increase in the permeability. And she was able to now build a model, a reduced order model, that turns this really complicated system to actually just a one-dimensional problem that she was able to demonstrate can allow you now to understand how the reactor variables change during this nanochemistry. So again, this now gives us some insight into how that nanochemistry can actually connect us back to a full reactor model. And I guess a big thank you to the Door School of, the Sustainability Accelerator Program, which I think is in the Door School, for supporting us on a project, connecting this to the actual full-scale reactor models. So please stay tuned, and we hope to have cool results for you within the next year. So towards those goals I mentioned to you before, we also wanted to understand how we can use some of the more exotic aspects of the chemistry to be able to understand some of the dynamics that are happening in this process, i.e. to be able to also innovate in creating new processes, like, for example, ways of using light to be able to drive iron oxide reduction. So my student Lauren has been working on developing a photochemistry setup for our light source in New York, where we've started effectively studying how in situ we can now watch these types of reactions under different reactive gas environments and things like that. And now, actually, just in the meeting before this talk, we were chatting about the exciting new results she's starting to get, exploring how the color of light potentially will allow us to understand this chemistry in a different way. So, you might ask yourself, you know, Professor Dressler-Murray, you're talking about this really fundamental science stuff. How does this actually translate to something you would actually roll out in industry? Well, to understand how to have an impact in this industry, we have to start out with a model system that can describe the interdependent driving forces that ultimately govern the reaction. So that allows us then to be able to measure and model the kinetics, and to be able to then build up these reactor scale models like I showed you in this talk. So with this, we can then start to incorporate techno-economic analyses, like some of you guys do who've been in this department, and start to explore how the science that I've been talking about now results in technological, not the other one, economical models and trade-offs that you would have to think of to be able to understand how to design something that would actually be cost-effective. And then, of course, we need to finalize everything by testing it out at a pilot scale, and in the case of steelmaking, at a demonstration scale. First, to prove that we can get this to work at kilogram scale, then at a kiloton scale, to be able to demonstrate to the field that we now have a cost-competitive technology. So these types of early stage problems and solutions are actually really vital to be able to have a path forward in some of these really emissions-heavy fields, even though, of course, as I've been sitting here talking, this sounds very, very fundamental science and not so applied. But of course, we need to have this type of work to be able to prioritize full industry decarbonization within the next few decades. So now I'm going to switch gears to a different direction in the metals extraction community, but still an important one that if you guys have been reading the newspapers, you'll probably notice has been more and more discussed in the papers. So beyond steel, when we look at rare earth elements, we find that rare earth elements are one of the critical materials out there that currently are really, really crucial to some of the up-and-coming technologies and technologies we already use and rely on, but that we currently actually don't have a supply of that can match the production that we need, other way around. But we can't produce enough to match the supply that we need. So this is showing you rare earth elements, which is one such critical material. Rare earth elements, you guys are used to that periodic table. You got the big table in the middle, then the little one that comes out. Most of the rare earths are in the little one that comes out. And one of the unique things about that little row that comes out is that, in fact, it has really unique electronic properties that, for example, can make some of the strongest magnets we have on the planet, permanent magnetic fields, that is. So that's really helpful for things like turbines or windmills. It also can make really good contrast agents for biological systems if we're trying to do medical imaging, and a whole host of other types of technologies. But today, the way that we make these is 96% in China at one of two mines. And the reason for that is because although rare earths are not actually rare, they are in very, very low concentration in most of the rocks that we find them, meaning that it's not really that cost effective to harvest them unless you put in a really, really large capital investment before you eventually end up with the system that you need. So China very early on put in a huge investment that really in the late 2000s, we discovered actually almost took over the entire global market. And there's been some political aspects to that I'm happy to chat about after the discussion. But ultimately, when you ask yourself, well, why can't anybody else get into this market? Part of the issue is that for this separation to happen, we start off with basically getting rocks out of the ground and crushing and crushing and crushing. Then we have a whole series of roasting and leaching with really, really acidic and dangerous chemicals. These are liquids, these are things that are getting into the groundwater, that are causing the actual life expectancy of people in the nearby villages to go down by quite a significant amount. In fact, near the Bayan Obo mine in China, they have a radioactive lake that is getting bigger and bigger because most of the deposits we have of these rare earth elements we only know about because they also come with uranium and thorium that are incredibly radioactive and hot. So the challenge is that although we actually have some of these deposits here, and this is showing you some of them, there are actually many more little stars that I should add to this plot. The domestic deposits that we have require different strategies to be able to enter the market. So that's because there are environmental needs, i.e. we're not in this country going to be able to put H2SO4 into drinking water. We also have some distinct ore bodies here that today our extraction techniques that are out there actually can't perform on. So even though we have rich deposits of these, we actually don't have accessible deposits that have production pathways within. So in my group, over the last, I guess, 2 years now, we've started developing a new one-step approach to be able to isolate rare earth elements from their ores. So this is showing you an X-ray fluorescence spectroscopy image of the native ore bodies before our treatment and then afterwards. And this is very preliminary data, very preliminary science, but what we've been able to show is that actually with one step, we can just go from straight rocks to effectively separating the rare earth elements from the host materials. So I can't say too much more about this, as this is still being prepared for our patent publication. But what I can say is that we are now, sorry, there's one more photograph that has to go here with our new student. But effectively, this is now showing us a new pathway that we've been developing where we now really are able to get the progression of these really, really complicated rocks to now something that is much less complicated, that ultimately we can start to, 5 minutes, so topic 1. Okay, might not get through the whole supply chain today. So this gives us now a view of kind of the opportunities available with this type of approach. So now I'll get into my second topic, and I think we'll have to skip the third one today. Well, I'll be happy to chat. There's like a discussion group after, right? So I'll be happy to chat defects and metals after. Here. So now we go from steel making and just extraction of metals to making actual replacements. So in general, to make a device, you take metal, you make it molten, you pour it into a mold, and you have all sorts of blacksmithing type processes like forging and cold rolling, hot rolling, that ultimately will get you to the properties you see. This has some constraints though, i.e. you have to be able to machine the material and you have to be able to find a material that has these set of properties that you're looking for. That isn't actually always possible. So metal 3D printing has started enabling a whole new host of designs that has never been possible before. So this cute little rocket engine up here, it's actually one single piece of metal. So usually that would be like hundreds of pieces of metals and other materials that are all welded together or printed together in various different ways. But in fact, by printing a metal part layer by layer, you can digitally manufacture the shape of the part and basically melt a little bit of your powder bed, one layer at a time, to create these really, really arbitrary shapes. So in fact, this is made out of a lattice material, where basically you have just the 3D structure of a material that goes in and out of itself that you would never make with machining tools today. However, there's some challenges that set that back that have made metal manufacturing with 3D printing not nearly as in the forefront as plastics 3D printing is today. And that is that to make this work, we need to be able to bring in a laser to rapidly melt the material, sometimes even vaporize it, generating these really, really strong rapid thermal flows of the fluids, as well as particles that get launched into the air and go splattering everywhere. Then we have rapid cooling that causes us to crack or have phase transitions, some of which go to weird materials that we don't really understand the performance of. And this happens every single layer of our print. So to be able to understand how metal 3D printing works, we need tools to be able to understand this. However, the methods that we have used to be able to see through a metal as it's printing have been rather limited. So X-rays have been able, over the last 10 years, to start to give us a view into how this works. We can with, this is the synchrotron down here. It generates the X-rays, and you'll notice the size of the synchrotron with respect to the size of the mountain next to it. This is in the lovely French Alps. By just basically coming in with an X-ray beam and looking through your metal, you can actually watch how this happens in real time. So this is what's called X-ray radiography, where now you're watching, this is the vaporized pool of the metal, or jet of the metal, that's going into the material and is very, well, it looks like slowly, but this is actually incredibly rapid. This is at like megahertz frame rates. You're now watching basically the metal get printed, and often these pores get left behind. Those pores, by the way, localize stresses and give rise to fracture that ultimately will cause this whole part to fail. So over the last several decades, these tools have been able to study how various different aspects of this technology generate different attributes and defects that ultimately we can actually kind of evaluate the trade-offs of and understand how, based on the different scan properties, i.e. the velocity of our laser and the power of that laser, we can now create a process map to understand what version of that will make a printable material versus not. But there's actually some stuff that's still missing there. In particular, looking at physical defects and mixing defects in alloy design. So in our work, we've built and developed new microscopes to be able to address these types of problems, starting with two types of defects, falling and mixing into more detail. So I'll go really fast because I think I'm on borrowed time now, but science behind balling is effectively that as you speed up your laser, effectively your melt pool, your fluid dynamics doesn't have time to catch up, and you end up with this disconnected set of droplets that form that is hypothesized to be the plateau-Rayleigh effect, i.e. the effect that causes your faucet to generate, if it's on really, really low, to take that cylindrical stream and turn it into basically droplets. But we've been able to demonstrate that actually at the really high speeds, in fact, this doesn't capture all the physics. And we've been able to start looking a little bit deeper into that and to demonstrate that there's actually some really fundamental science aspects. That if you just look at the fluid dynamics of this process, in fact, you don't need instability criteria to be able to describe this. So ultimately, this is now giving us kind of a new look at this science that is now allowing us to understand the driving forces that describe different phenomena that we can use to attribute what's good versus different types of bad printing might look like. So in the alloy mixing field, we can now start to look towards even more strange types of parts we might be able to make, i.e. now looking at parts where we could create an alloy that changes as a function of space, i.e. if you had an arm of a pendulum, where now you could take a load-bearing part and the part that does not experience the load, and you can actually give them different compositions and properties, because actually you could design your material spatially as well as in terms of just the properties. So this type of 3D printing is called functionally graded materials. And as you can see here, you can think of this as basically taking two elemental powders, and in your actual printing process, now you are in situ alloying the material to create whatever local alloying conditions you want. So conventional X-ray radiography would look something like this, where we now started to be able to trace this by demonstrating how effectively you're seeing, it looks like smoke here is kind of going over this. The dark region is actually the alloyed material that we're now bringing in at these high velocity conditions. And you can actually now see that the fact that it's darker at the top is now bringing in the copper from the top layer. So we can now start to track these types of mixing events. And we developed a new microscope at X-ray free electron lasers, that world's fastest and brightest X-ray laser, one of which we actually do have at SLAC up the hill. And we've been able to create a multi-scale microscope where we can watch at that full scale of the whole melt pool, as well as that really zoomed in scale of actually watching the individual vortices that create these mixing events. And we've been able to now start to build a model to understand how the length scales over which mixing can occur are driven by ultimately different velocities of the fluid dynamics that drive. So I'm going to skip this section and include it at this point. Excuse me. So to summarize, I started off talking about my group's work on sustainable steelmaking from an understanding of the really fundamental science of hydrogen-based direct reduction, and then looking towards building models of hydrogen-based reactors. I then gave you guys an introduction to some new exciting work that we have going on solvent-free rare earth element extraction. And then I also mentioned to you some of our new work on metal 3D printing, building microscopes to understand now how to build the next generation of parts, not just the metals that we use to make. And I didn't quite get to talk about dislocations. I'm happy to take questions that you want to ask. Thank you very much, and happy to take any questions.
Great presentation. I felt like we were going back and forth between. Sorry, I felt like we were going back and forth between planet Earth and Star Trek, and back to Earth and back to Star Trek. Your story is very interesting, positive, and inspiring, and we hope you the greatest success in the future. So we're watching for it. I have a feeling that you might break the record, like it or not, of what was it, 17 or 18 years to go from conception to large scale manufacturing. Anyway, so we only have time for maybe one or two questions in the room before we adjourn. Any questions?
I'll take the microphone back.
Go ahead.
Okay, any questions? Any takers? Go ahead.
Can you speak on the metal 3D printing? I've heard a little bit about kind of multi-reactor processes where they try to reintegrate these defects. Can you speak to that at all?
Yeah. So for those of you online, we asked about basically whether we've done work on looking at annealing and things like that, or post-processing for net shape manufacture. So we personally haven't. We're a little new to this field. That said, a lot of people do study that. It's a slightly different process. We've studied annealing under different contexts, but in general, one of the biggest challenges there is that you, when you have these rapid cooling processes, you actually also trap a lot of residual stresses. So the issue with annealing is that when you anneal, you don't have any guarantees you're going to end up with the same shape you start. So this is the challenge of, it's called net shape manufacturing, is that you actually have to be very, very careful and deliberate with how you even strain your sample as you're solidifying it to make sure that when you then anneal it, you're designed to anneal to the shape you want. i.e. you 3D print the wrong shape, knowing it'll go back to the right shape. We haven't done that because we're looking at a much smaller length scale, so we don't think about it more as like a, how do you print this part, but it's definitely a big part of the field, and happy to chat.